All right, have a guess what this video is about. The celestial theodolite. And this came up again in the debate between Jaron and Whitsett, and Whitsett brought it up as one of his major proofsies. So I thought I should address it properly. So what is the celestial theodolite? Well, basically, it's a method that a dude named Mike Heffron came up with. It's a camera set up pointing at a mountain and taking time-lapse images of the stars as they set behind that mountain. I'll let Whitsett explain it a bit more.
So I would say one of the really strong pieces of evidence that we live on a plane is something that we recently found out, which is if you actually take angle measurements to stars, say from a ground and from the surface of the Earth, you're going to see that the star gets occulted by the mountain. As soon as that moment happens, you can take the time, you can measure that angle, and you can compare it to the angle of, like, say, in Stellarium. At that exact time you took the time measurement, as soon as the star was occulted, you can then go to the mountain, compare that angle, and it is as if it is planar geometry. It matches perfect. The flat Earth prediction to that star matches perfect, whereas the globe, it would be an entirely different position, many degrees different, and the issue is that they would then have to try to claim refraction, but the star has already been occulted prior to the measurement, so refraction can't even be applicable. So the actual occultation of the star in relation to topography, and the guy that initially went and made this measurement was a glober. He went out there and he saw that the prediction is, you can predict it perfectly with flat Earth, doesn't match the globe at all, and refraction didn't work. He ended up leaving the globe.
All right, doesn't match the globe at all, hey champ. Now, all right, just to be clear, there is no actual measurement of angles happening here. We're just recording the time that the star sets behind the mountain. So, just a brief segue to my first video on the celestial theodolite a few months back. And you remember I put out a friendly wager that the measurement that Mike Heffron made with his shitty level transit was wrong. And if it was measured properly, he would have measured close to the globe prediction instead of the flat Earth prediction. Well, just for shits and giggles, apparently about a week later, his brother came out to his place with a decent piece of equipment, measured the angle to the mountain, and what do you know, it matched the globe. So of course, that's gone from flat Earth proof before the measurement to, never speak about this again after the measurement. Anyway, back to the process. As I said, there's no actual measurement of angles happening here because obviously that would confirm the globe. So what they do is point a telescope at a mountain and start recording a time lapse. Then after a couple of hours or whatever, they go back and look at the footage and record the exact time down to the second for when a particular star was occluded by the mountain. They go and set that time in Stellarium, and then for some unknown reason, they move the Stellarium observer to the peak of the mountain, which is not where the observer is. And then again, for some unknown reason, they turn off the atmosphere in Stellarium. And then record the raw geometric angle to the star, as opposed to the refracted angle at which you would actually see it. And then step 4, do a simple arctangent, sort of rise over run for what the angle to the mountain should be on a flat Earth. And then step 5, the conclusion is that this angle supposedly matches the geometric angle given by Stellarium in step 3. And the conclusion, therefore, Earth is flat. And here's the example that kicked off the whole thing. Dr. Heffron lives in Colorado, about 50.7 kilometers from Pikes Peak, and he recorded a star in the Aquarius constellation setting behind Pikes Peak. So you've got all the details in the top right there. So if we follow the celestial theodolite procedure, we have to turn the atmosphere off because apparently we live in a vacuum. And we also move the observer to the mountain peak because we can just fucking teleport. And then we grab the elevation angle out of Stellarium. And it's 2 degrees and 33 minutes. And then we compare that to the raw angle on a flat Earth, just using trigonometry. And that would be 2 degrees and 31 arc minutes. So we're 2 arc minutes off, which, I guess means we must live on a flat Earth. But what about the globe? Well, on the globe, we don't have to do stupid shit like move the Stellarium observer to some place where the observer isn't, and nor do we need to ignore the fact that we have an atmosphere. So, to calculate the prediction for the globe. We first calculate the drop between the observer and Pikes Peak, and that's 201.7 meters, and then take that into account to get our geometric angle to the mountain, which is that 2 degrees and 17 minutes there. Then we apply a typical value for refraction of about 2.4 arc seconds per kilometre, and that adds roughly 2 more arc minutes. So the predicted angle to the peak is about 2 degrees and 19 minutes on the globe. So at 18:27 and 25 seconds, with refraction turned on and the observer position where the observation was actually fucking made, Stellarium gives an apparent altitude angle of 2.3153 degrees, or very close to 2 degrees 19 minutes. And again, this is in excellent agreement with our prediction of a touch over 2 degrees and 19 minutes. But in coming to that prediction, I actually found what I consider to be a bug in Stellarium. So what I found was that Stellarium applies the same amount of refraction regardless of whether you are at sea level or on the top of a mountain. And obviously, if you're on the top of a mountain, then you're looking through a lot less atmosphere, so the amount of refraction should be less. So all I've done here is find a calculator online to give me the atmospheric pressure at Dr. Heffron's elevation, which is about 2,074 meters, and then plug that pressure into Stellarium. Right, so why did this celestial theodolite method give a result that was reasonably close to the raw flat Earth angle? And is that a coincidence? Dun dun dun! So let's try to reverse engineer this celestial theodolite result and try to come up with a formula for why it would match the flat Earth angle even if the Earth is in fact a globe. So we're going to have a look at all the components that go into each calculation. So all right, starting with only the distance to the mountain, which was 50.7 kilometers, and the delta height, so the height of Pikes Peak minus the height of the observer, minus the drop. Then we add in terrestrial refraction, and we calculate that any star occlusion on the globe would occur at the same apparent height of Pikes Peak. And that was that 2 degrees and 19 minutes that we worked out previously, right? So this means that the apparent angle of the star at that time also has to be 2 degrees 19 minutes. But this figure includes some amount of astronomical refraction. But how much? So the cool thing is that Stellarium is actually open source. So not only can you have a look in the source code to see that it is clearly using a globe, but for the purpose of this video, we can find the formula that Stellarium uses to give you the geometric unrefracted angle to the star if you know the observed angle. So here's the code here, and if we plug in all the variables, we get an astronomical refraction correction of 13 minutes and 20 seconds, so almost a quarter of a degree. Right, so we know that the observed angle to the mountain and the star at the time of the occlusion is 2 degrees 19 minutes, and that includes 13 minutes of astronomical refraction. So that means the geometric altitude of the star from the observer location is about 2 degrees and 6 minutes. All right, the next step to reverse engineer this thing is to mimic moving the observer to the mountain peak. So this will raise the altitude of the star by 1 degree every 60 nautical miles. And so the mountain is 50.7 kilometers away. So this raises the altitude by about 27.5 arc minutes, which gives you a final result of 2 degrees, 33 minutes. And that's very close to the value that we got out of Stellarium a few slides back of 2 degrees, 33 minutes. So yeah, we've successfully mimicked the celestial theodolite process. Right, just to recap. So the goal was to use the globe to try and come up with a way to determine why this celestial theodolite method gives an angle that's, you know, almost matchy-matchy with the raw trig angle on a flat Earth. And once we know that relationship, we can easily find an observation where the method will not work. Yeah, so this single example of a star sitting behind Pikes Peak isn't the only star that was captured, nor is it the only peak that was used. So Dr. Mike has a PDF on Space Audit's website that gives details for a total of 39 observations across 7 different peaks. Now, obviously, there'll be a link to this PDF in the description. Here's page 2. And here's the last page. And I want to draw your attention to this last mountain called Greenhorn Mountain. Now it's 132 kilometers away from Dr. Mike. And the 2 stars that he observed were more than 10 arc minutes apart, according to Stellarium. So there's very obviously a problem with the observations here. So we're basically going to ignore these 2 observations in the analysis. All right, and I've done some really cool analysis on these observations. So if everyone can pepper their Angus, the next screen is super freaking cool. Ready? Boom. All right, this is probably the coolest, but also the nerdiest thing I've done this year. All right, so in the last few slides, we've been able to reverse engineer what the celestial theodolite angle should be, from on top of the peak that's doing the occluding, with the atmosphere turned off, and only using the distance to the mountain and the delta height as the variables. And what you've got on this slide is, for every possible combination of distance and height, I've worked out the celestial theodolite angle and the raw flat Earth angle, and the result that you see on this graph is just the difference between those 2. So it's kind of like the celestial theodolite error. So first thing you'll notice is that yellowy white curve going from the middle left to the bottom right. So for example, if there was a mountain that was 70 kilometers away and about 1,500 meters higher than me, that's right in that sweet spot. And I would expect the celestial theodolite angle to be a very good match for the raw flat Earth angle. However, if there was a mountain 30 kilometers away and only about 200 meters higher than my elevation, then I would expect the celestial theodolite angle to be absolutely nowhere near the raw flat Earth angle. So just to be clear, this graph is how well I expect the celestial theodolite process to perform if the Earth is in fact a globe. So obviously I've also plotted the mountains that Dr. Heffron used based on this magnificent heat map. I would expect that Pikes Peak and Mount Rosa to give reasonably good celestial theodolite predictions. Green and Blue Mountain a little worse. And then Cheyenne Mountain and Blodgett's Peak to be significantly worse. All right, so let's look at the actual observations. And here's another cool little graph. So for each mountain, the blue rectangle is the range of celestial theodolite angles. So turning off refraction, teleporting the observer, and getting the geometric altitude angle. And the little red crosses are the raw flat Earth angles. So first thing to notice is that none of the little red crosses are inside the blue rectangles. Right? If they were inside the blue rectangles, that would mean that the celestial theodolite results were a good match for the predicted flat Earth angle. But what this graph actually shows is a reasonable correlation to the predictions that I made from the heat map. So like I said, we've got Mount Rosa being pretty much spot on, as the reverse engineering would suggest. Green Mountain swaps places with Pikes Peak. Blue Mountain coming in next, and then Cheyenne Mountain and Blodgett Peak, as predicted, were rubbish and don't support the celestial theodolite at all. Right, but how well do these observations match the globe? Or remember, we're not doing stupid shit like teleporting the observer or pretending we don't have an atmosphere. So in this graph, again, the blue rectangles represent the apparent altitude of the star at the time of the occlusion from where the observer actually was at the time. And the red crosses are the predicted angles assuming a globe. All right, so first thing to notice is that Pikes Peak and Cheyenne Mountain are within the blue rectangles. So that's a very good match for the globe there. Then you've got Blue Mountain missing by half an arc minute, which is fuck all. Mount Rosa and Green Mountain off by about an arc minute each, and then Blodgett Peak is the worst of the globe predictions, off by 1.8 arc minutes. And I shouldn't have to remind you that the original celestial theodolite example that we analysed at the start was off by more than 2 arc minutes. So if a 2 arc minute error is proof of flat Earth, then the worst result from the globe predictions is less than that. So hopefully it should be pretty clear that the globe objectively makes better predictions than the celestial theodolite and doesn't have to make silly assumptions. All right, so let's listen to Whitsitt have a little cry, and then we'll deal with his objection.
And so what all the globe proponents have been trying to do is claim refraction, trying to find out any way they can to claim refraction, and they can't with this though, because it's occulted. It isn't there. It's not even there to talk about, to invoke refraction. It's not even applicable.
Alrighty, that is of course absolute rubbish. It is not possible to eliminate refraction from an observation through the atmosphere. All right, and I just think this shows that the Flurfs don't have the right picture in their mind of what refraction does. Right, so here's a side view of that last moment before the star sets. All right, so we've got the star way off to the left, and the light coming from the star is curving through the atmosphere, just grazing the top of the mountain and then into the camera. That's the orange line. It's the physical path that the light takes. But our camera doesn't know that the light has taken a curved path. All it knows is what angle the light comes into the lens at, and that's the red ray, so 2 degrees, 19 minutes. So in the very next frame of the video, the star's dropped a tiny little bit, and that curved path now physically hits the mountain. This idea of dispensing with refraction or negating refraction because the light is blocked by a physical mountain is very silly. So all you're doing is recording the time that the refracted path is blocked by the mountain. So here's what it looks like geometrically if we assume straight lines to the mountain and the star. Like if you somehow pulled a string tight between you and the star, then that line would be blocked by the mountain long before you've seen it disappear. And that's because refraction lifts the apparent position, and the amount of apparent lift is a function of the distance. So you can see that little orange arrow there just above the mountain. The curved path of light from the top of the mountain comes into the lens at 2 degrees 19 minutes, which is 2 arc minutes higher than its geometric position. While the starlight has traveled about 1,200 kilometers through the atmosphere, so its path has curved a lot more, and it's lifted up by about 13 arc minutes, which is that green arrow. All right, so one simple question for Dr. Heffron, for Alan, for Shane, whoever else. It's really silly to try and claim that this method eliminates refraction as a variable. And I think the easiest way to expose that is to ask Whitsitt and or Dr. Heffron or Alan to answer this question. Does refraction affect the time the star is occluded? They all agree that refraction is a thing. They would all agree that the apparent height of the mountain changes during the day. So the answer is obviously yes. So if you change the time of the occlusion, then you change the geometric angle you pull out of Stellarium. All right, now the follow-up question. If you claim that you've eliminated refraction, why don't the results match perfectly? If you've just got straight line geometry all over the place and no atmospheric variables, then where does the 2 arc minute error come from for the Pikes Peak observation? Where is the variability? If it's just plain geometry, you should be exact. So obviously the answer is that you can't eliminate refraction. Refraction is a factor, and it's impossible for it not to be a factor. Anyway, getting back to the glory that is my heat map, my man Jesse, Path of Light, had already worked out the relationship between distance and delta height, and he proposed an observation that he knew would not give a good celestial theodolite result. So from his location in Washington State, he chose to look at a mountain called Blyn Mountain. And here it is on Google Earth. That's Jesse on the left and Blyn Mountain on the right. It's 41 kilometers, and the difference in height is about 640 meters. So if we plot Jesse's observation for Blyn Mountain on the heat map, we predict that the celestial theodolite will give a shit result. So here's a screen cap from Jesse's video. Blyn Mountain is a little bit to the right where the radio tower is. We've identified 2 stars. The star we're looking at is HD 192947, and the timestamp is in the bottom right. And here are the screen caps from Stellarium showing an altitude angle of 0.6813 with the observer placed on the peak and the atmosphere turned off. That equates to about 41 arc minutes. Then we do the raw trig for the angle on a flat Earth, and we get 54 arc minutes. So it's about 13 arc minutes off, which is absolute rubbish. All right, so the final recap. All right, so we worked out that the celestial theodolite results are a function of the distance and the delta height of the mountain. And the results might seem persuasive if the particular distance and height combination falls into that sweet spot on the graph. And I want to be clear again, the sweet spot was predicted using the fact that the Earth is a globe and has an atmosphere. And finally, without the silliness of moving the observer and ignoring the atmosphere, the occlusion timings are a much better match for the globe.